Hello all, welcome to the webinar series of IEEE Joint Chapter of MTT-AP-EMC Societies at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMS, that is one of the Institute of National University of Science and Technology, Islamabad, Pakistan. I am Dr. Nusharan Shoaib. I am currently the chair of the chapter. We have started this series in March 2020 in the view of pandemic 2019. And we have conducted a number of webinars under this series. This webinar is also the part of that series. The institute, which is also known as RIMS, is located in Islamabad. Islamabad is the capital of Pakistan. Pakistan is and also among the beautiful capitals in the world. It also has a business hub and also have the natural beauty as well. I also would like to mention that our chapter is also planning to hold the Pakistan first dedicated RF and microwave conference next year in 2021. The dates will be communicated very soon. That conference will be held in Islamabad in NUST H12 campus. I would like to request all of you to submit the papers and we'll be happy to host you in Islamabad. So as I said, National University of Science and Technology is located in the Islamabad campus. It has a number of campuses and Islamabad campus bird eye view is shown here. It has also other campuses as well in different cities of Pakistan. Our institute, which is also known as RIMS, is located here. So Research Institute for Microwave and Millimetre Studies is basically a unique postgraduate institute that offers MS and PhD program in electrical engineering with specialization in RF and microwaves. Apart from just coursework, we also have the RF and microwave research and measurement facilities, including anechoic chamber that works up to 40 gigahertz. We have EMC-MI lab, a pre-compliance lab for EMC testing. We also have a microwave research and antenna lab and also an in-house PCB fabrication lab. So by having all these facility under one roof, the student this will give the student an opportunity to have an hands-on experience in addition to their classwork. So today in our webinar series, we are very pleased to host Professor Nick Rittler. He's a fellow of IEEE. He's from National Physical Laboratory, UK. And the title of the webinar is Developing National Measurement Capability for Millimetre-wave and Terahertz Frequency Ranges. Professor Nick Rittler received the BSc degree from King's College London, University of London, UK in 1981. He is currently the head of science in the Department of Electromagnetic and Electrochemical Technologies at the UK's National Physical Laboratory. He is also an honorary professor at University of Liverpool, UK, and a visiting professor at University of Leeds, UK, and also a visiting professor at University of Surrey, UK. He is also a non-executive director of LA Technologies Limited. He is a fellow of IEEE, fellow of IET, and fellow of Institute of Physics. He has almost more than 40 years of experience working in industrial, government, and academic research establishments. His main area of interest is precision high-frequency electromagnetic measurement, ranges from 1 kilohertz to 1 terahertz. I'm also very honored to work with him as a PhD student during my PhD studies when I visited him in UK. So without any further delay, I request Professor Nick Rittler to please proceed ahead and start the webinar. Thank you.
Okay. I'm wondering if you can project my my title slide.
Yeah.
Okay.
So, okay. Professor, can you share your desktop again?
Sure, sure. Can you see something yet?
Yes, I can see. So I am putting it live now. So yes, please go ahead. You are live now. Thank you.
Okay, very good, very good. Well, thank you very much for the introduction, Nusharan. I do appreciate that. And good afternoon, everyone. It's a real pleasure and a privilege for me to give this talk today at this IEEE MTT AP EMC joint chapter event. And so, yeah, I'm delighted to be able to give this talk. I'll be describing basically a selection of activities from an ongoing programme of work at my institute here in the UK, which is called the National Physical Laboratory, and we're developing a national measurement capability for millimetre-wave and terahertz frequency ranges. My background is very much measurements, so this talk is going to focus very much on issues that relate to measurements and quality of measurement, etc. I'd first like to explain why this work is being done by my institute in particular. And so I'll say a few words about the institute, National Physical Laboratory, or NPL for short. We are the UK's National Metrology Institute. Now, metrology is the science of measurement, and so we're a government-owned institute that focuses exclusively on understanding and disseminating measurements. We've been operating since the year 1900, so we've been around for 120 years. We currently have about 1,000 members of staff on site, along with many visiting researchers and academics that visit us from time to time, as indeed was mentioned earlier by Dr. Shoaib about his time of visiting us here at NPL. We're currently divided into 9 different scientific departments, which I'm showing here listed on this slide. And we cover many areas of the physical sciences. I won't read them all out to you, but there are things like data science, medical physics, environmental science. And the one at the top there, the electromagnetic and electrochemical technologies, that's the department I work in, and that's where the work that I'm going to be describing this afternoon to you, that's where it sits within my institute. My role within NPL, I'm currently the head of science for my department. We have about 100 scientists and engineers working on electromagnetic and electrochemical technologies. I've worked in the area for nearly 40 years. I've worked in industry, in academia, and also now in government research, which is where I've worked for the last 20 years. My work really goes right the way from low radio frequencies into the terahertz regime, so covering frequencies typically from a few kilohertz to a few terahertz. And my main focus is on achieving accurate and reliable measurements. This is what my institute is all about, not just buying equipment and using it, but understanding the equipment and understanding how good the measurements can be that the equipment achieves. So that's my background. In fact, I've shown there my IEEE fellowship citation relates to traceability for precision measurements. So this is my background. I'm going to start off with 2 very simple questions, which I will answer myself. The first question is why should there be a talk at this chapter meeting on measurements? Well, my answer to that is very simple. Measurements are important. That's very important to emphasize that. And so the following question, why are measurements important? Well, it's because we need measurements both in our day-to-day life and in our scientific laboratories and throughout everything we do. So, for example, measurements help us to make decisions. We can assess performance. For example, if we have a device like an amplifier with a specification, we can actually measure the device and assess its performance with respect to that specification. So measurements play a vital role in the so-called customer-supplier arrangement. So, for example, if you're selling something, then you need to make sure that you're selling what you claim you are selling on your website or whatever. The other side to that coin is if you're a purchaser, if you're buying something, you want to make sure that what you actually buy is what you're expecting to buy. So we use measurements to assess the performance of things that are being sold and things that are being purchased. So behind measurements, there's a strong drive of commerciality in terms of, you know, global supply and demand of products and services. So we need measurements in particular when we're pushing the boundaries of science and technology. So I expect many of you are working at institutes where you're doing research to generate new science and new technology. Or when we do generate new science and technology, we need measurements to underpin that science and technology so we can prove the claims about the performance of the new technology. So for example, if we developed a new amplifier that say worked at 1 terahertz, how do we know what the gain of that amplifier is? Well, we can only really demonstrate it through measurements. So measurements prove performance. So it's essential that measurements are available for the new science and technology that's generated generally in the scientific community. And so this usually means developing new measurement capability that goes alongside the new science and technology that's being developed. And I'm going to illustrate that in this talk with a particular application. So whilst in our area of, say, high frequency microwave science, where there's new advances being made in that area, we need new measurements, new types of measurement to ensure that the measurements meet the requirements of the new science and technology. So it's the new advances in measurement capability that are the subject of my talk. And I'm sure you have work that you're doing where you're doing new science and technology, or think in the future about perhaps what measurements you might need. My talk will be in two parts. I'm showing it here. The first part is what I call filling the gap in the electromagnetic spectrum which exists between microwave frequencies and photonic capabilities. So that's going to be the main thrust to my talk. However, I'm going to include a second part which is looking at general aspects of measurement, and in particular what we mean by accuracy, and also what is the importance of having measurements that have what we call traceability. So I'll say a few words about that as well in this talk. So the first topic, filling the gap between microwaves and photonics. What do I mean by that? Well, I'll put up a slide which is a kind of a schematic of the electromagnetic spectrum. You can see the line going across the middle, which shows increasing frequency as you go from left to right. And of course, at low frequencies, at RF and microwave frequencies, we have many applications in electronics that we use day to day. And they use frequencies in the kilohertz, megahertz and gigahertz frequency ranges. Then on the right, you'll see what I've labeled as photonics applications. So this is where people are using optical techniques, visible light, etc., infrared, to carry out science and technology. And you'll notice in the middle there, there's a gap between the two, which I've labeled as terahertz. Also applies to millimeter waves as well, where really the electronics techniques start to really kind of fall over really in terms of ability. And similarly, the photonics techniques don't really work well either in that region between the electronics and photonics. So we talk about a gap in the electromagnetic spectrum between electronics and photonics. And in recent years, there's been much activity, if you like, new science and technology that's been exploiting frequencies in this gap region between electronics and photonics. And so with that new science, then that's motivated me and my colleagues and at similar national laboratories around the world to generate measurement capability in that gap region, in the terahertz region. So there are many applications now emerging using millimeter wave and terahertz frequencies. I'd just like to show a few of them on some slides now. Electronics, there's a big push a few years ago to develop electronics, amplifiers, integrated circuits, etc., that would work at these frequencies. And the illustration shown there is a 1 terahertz monolithic integrated circuit that was developed by Northrop Grumman that gave amplification at 1 terahertz. So that's some very exciting electronics research. There's also applications in radio astronomy. Recently, a a large telescope has been launched in a desert in northern Chile, which called the Atacama Large Millimeter Wave Array, which is using frequencies all the way up to 1 terahertz to make astronomical observations of the universe, etc. More relevant to our everyday lives, certainly up until recently with air travel, was use of security systems where they would do millimeter wave scanning. So that's a very commercial application of this sort of technology. And also space applications. Agencies such as ESA, the European Space Agency, use millimeter waves and submillimetre waves in airborne radiometers, etc., to do Earth observation and looking at climate change and so on and so forth. So these are also using these parts of the electromagnetic spectrum. One that I haven't put up, but I think I'll mention as well, is the use in future communications. I'm sure we're all familiar with the current rollout of 5th generation 5G communications that's happening now. Well, researchers are already beginning to look to, what will come next, what will be beyond 5G on the technology roadmap. And so researchers are starting to use these frequencies, millimeter waves and terahertz, to help roll out technology that will take us beyond 5G in the coming 10 or more years. So again, this is a very exciting use of this part of the spectrum and will benefit us all and our children in the years to come. So what new measurements are needed in this region as we go from gigahertz frequencies up to terahertz? Well, I'm going to pick just 3 types of measurement. There are many others, but the 3 that I'm going to choose are waveguide measurements, measurements of electromagnetic materials, and also measurements on planar circuits, on wafers. The reason I've chosen these 3 is they all rely exclusively on the use of vector network analyzers, and one technique will lead to the other. So you'll see that the work on waveguide enables the work on materials, and it also enables the work on wafer measurements. So I'm going to go through each of these 3 measurement areas and show a few slides. So the first one for waveguide measurements, I'll say a little bit of background about what we mean by waveguide. I'm sure you're familiar with metallic waveguides. There's 2 shown here on the right in the picture. This is waveguide that is fairly large in size, and in fact these waveguides date back to way back into the middle part of last century, when they were first used commercially and in various applications. The first popular waveguide was used for frequencies of around about 10 gigahertz, so centimetre wavelengths. And so the aperture size of the waveguide rectangle was typically 20 or thereabouts millimeters in width. And it's that defines the bandwidth of the waveguide for the signals that it can propagate. Waveguide is inherently narrowband, so it generally only covers frequencies within an octave, so a 2-to-1 ratio of frequency. And so as the frequency changes, you need to change that aperture size to accommodate the range of frequencies that you want to be dealing with. So for example, if we go to higher frequencies, going up from 10 gigahertz, as we go higher in frequency, the dimensions of the waveguide get smaller and smaller. So for example, when we get to 200 gigahertz, the waveguide has become really quite small, and I'll show you it there on the slide on the left. You'll see what is effectively a slab of metal, and in the middle is a tiny rectangle. This is the waveguide. All those other circular holes that you can see on the face of that waveguide interface, they're all alignment mechanisms. So they're used to help position that rectangle, that the waveguide itself, when it joins to other pieces of waveguide. So when you're making circuits out of components in Waveguide, you need to make sure they all align so that you minimize the mismatches. So the key thing to look at here is the rectangle in the middle, which no longer is those 20 millimeters that we needed for 10 gigahertz. We've now reduced the size to round about a millimeter so that it'll propagate frequencies of the order of 200 gigahertz. And of course, we can extend that further to higher frequencies. If, for example, we take the frequency range up to 1000 gigahertz, which of course is a terahertz, then the aperture of the waveguide has become smaller still. In fact, the aperture is barely visible on that waveguide shim you can see there. I'll point it out for you with an arrow. That tiny speck in the middle is a rectangular aperture. And the dimensions of that aperture are 250 micrometers by 125 micrometers. So really very small and only just visible with the human eye. What we do with those when we have them in my lab, because we're very interested in the dimensions of that aperture, it's the transmission line that we're using, so we want to know how good it is. We look at it under a microscope, and here is an image of that same waveguide aperture now shown under an optical microscope, which we took this picture whilst we were measuring it dimensionally. So in metrology, we like to explore the dimensional imperfections in these waveguides. In other words, how imperfect it is with regard to a nominal rectangle, because it's the imperfections that lead to measurement errors when we use these structures as references in our measurement systems. So it's very important we can characterize these structures so that we can predict and understand their electromagnetic behavior. So the characterization is done primarily through dimensional measurements. So we have a lot of dimensional measurement capability on site here at NPL to measure these sorts of structures. So here you can see one of the systems we use. On the left there you can see the 1 terahertz waveguide, which is really a thin section of waveguide, and it's being probed with a contact stylus attached to a coordinate measurement machine. So the full system is shown on the right, which is the system with controller, and then when you use it you put the waveguide into the operating stage and then it's probed, usually using an automatic probing system, to determine the dimensions of the waveguide. I mentioned earlier that it's not just the waveguide that is of importance, but it's also the alignment. And I mentioned those circular holes are used to align the waveguide so that when it joins to another section of waveguide, there isn't a large mismatch. This becomes of paramount importance when you get to these very, very high frequencies. Because the aperture of the waveguide is so small, then a small misalignment of even say 10 microns can give you a very, very large reflection coefficient. So in terms of measurements, this is an undesirable property, having large reflection. In terms of use in systems and components, a large reflection is undesirable because you're losing power, and power at these frequencies is already very scarce. It's difficult to get sources with high amounts of energy at these frequencies, and so to lose say 50% of your energy just because of a mismatch is not tolerable when you do systems design at high millimeter and submillimetre wave frequencies. So when we look at these waveguides, we're interested in two things. It's the apertures and what we call the flanges, in other words, the connection mechanism. And these have been recently specified in some new IEEE standards that were published a few years ago, aimed specifically at waveguides used above 100 gigahertz. In fact, they list standards going to at least 3 terahertz in those documents. And in fact going above 3 terahertz as well. I've listed the important parameters when we characterize waveguides. The first two relate to the aperture, in other words, understanding the width and the height of that rectangle we were looking at earlier. And the other thing is the alignment, which is where these circular pin holes and pins come in, and then we're looking at whether the aperture is fully aligned, and typically it can be displaced laterally or vertically, or it can be rotated with respect to a reference. These are all three undesirable features. The IEEE standards I referred to, these are title pages of each of the three standards. The one on the left, which is the first part, looks very much at the waveguide apertures. So it lists waveguides, as I said, going to 3 terahertz and above, what their dimensions, their nominal dimensions are in terms of defining the waveguide aperture. The second part, which is shown in the middle there, looks at the interfaces. In other words, it looks at the dimensional tolerances on the holes that one uses to align the waveguides during connection. And the part 3, shown on the right, looks at what we call uncertainties. In other words, how well these systems perform when you bring the two parts together, the apertures and the alignment mechanisms. So the third part really helps us to specify performances for these sorts of waveguides at these frequencies. I'm going to just show you a couple of slides that are extracted from these standards. So with the part 1, the one looking at waveguide apertures, there's some work inside the standard on aperture tolerances. So on the right there, you can see a rectangle shown in a dashed line, and then calculations are done when that rectangle may be, for example, of a height that is more than the nominal value or less than the nominal value. And similarly, the width, where the width might be wider than the nominal value or narrower than the nominal value. So the standard contains lookup tables and plots, which you can see on the left, which are plots of a reflection that are generated by these dimensional imperfections. So as the shape and size of the waveguide aperture changes from the nominal, then it generates a reflection, and that's shown in the graphs on the left in this slide. So one can use that to predict performance from observed imperfections. When we go to the second standard, the part 2 standard, where we're looking at what we call flange or interface tolerances, there's similar plots that describe what happens when the waveguide is displaced laterally or vertically, and that's shown here on the right, where you can see a rectangle in green and one in blue, and they're not quite aligned in terms of their lateral position, and that will generate a reflection coefficient. So the reflection or return loss is shown on the left for different types of displacement. So once again, we can predict from observed lateral, vertical and rotational displacements, we can predict the electrical performance of these devices when they're used in measurement systems. So the way we operate is we fully characterize our devices, the test ports that we have on the measuring instruments, the standards that we use and the devices that we might be measuring. We can fully characterize those and then turn that into a measurement capability. So on the next slide here, I show a measurement capability that we've established for this type of work. This is a vector network analyzer, which you can see in the background there. It's a standard unit that you can buy from different manufacturers. And in the foreground, the black boxes, if you like, are frequency extender units that take the frequency from the network analyzer as a fundamental, and then it generates harmonics from that fundamental, and the measurement system, which operates between the two extender heads, will do measurements at one of the harmonics of the fundamental of the network analyzer. So for example, if the network analyzer is giving out a frequency of say 10 gigahertz or let's say 20 gigahertz, then the extender heads might be working off the 10th harmonic of that frequency, which would be 200 gigahertz. So these extender heads allow the network analyzer to move right up into the millimetre and submillimetre wave frequencies. And the system I've shown there is one that we've set up at one of the universities in the UK, at the University of Leeds, which is a university that I partner with in my work. And we have a system there that operates to 1.1 terahertz. So it uses the waveguide band that operates from about 750 gigahertz right the way through to 1100 gigahertz. And that's the system operating there. We run all the computations based on dimensional imperfections and other performances of the system, so we can predict the overall measurement system capability. So here is a slide showing some of those assessments. On the left is an assessment of the dynamic range of the 1 terahertz network analyzer, and we're looking there at transmission as a function of frequency, and you'll see that it's sitting round about at minus 60 dB isolation. So that gives us a discrimination or a dynamic range of about 60 gigahertz at this 1 terahertz waveguide band. When we run the computations on waveguide misalignment and aperture, etc., as I've just described, then we can predict the overall accuracy of the network analyzer. And typically, if we're measuring, say, an attenuation of about 30 dBs, then we would expect an accuracy of about 3 dB in that 30 dB. So about 10%, which doesn't sound very good as far as a measurement goes. So normally with a network analyzer, we would have much more accurate measurements than that. But the setup here has to recognize that we're working at 1 terahertz. So we're not working with normal size waveguides, we're working with tiny waveguides. The slightest misalignment will give rise to an uncertainty, an error in the measurements. And similarly, the harmonic multiplication is such that the power coming out of the source at these frequencies is very low power. And so the dynamic range is not as good as one would normally have with a network analyzer operating, say, at centimetre wavelengths. So this is really state of the art, and so on the one hand, the accuracy is not as good as we get at the centimetre wavelengths, but on the other hand, this is if you like, a world first to have capabilities at these terahertz frequencies using electronics techniques that were more familiar and more happy, if you like, at RF and microwave frequencies. That's all I'm going to say about waveguide. I'm going to move on and say something about materials measurements, because the setup I'm going to describe for electromagnetic materials relies on these waveguide measurements. So a quick overview of electromagnetic materials measurements. Traditionally, the techniques that have been used for many years are things like open resonators, which work very well at narrow bands at millimetre-wave frequencies. Also quasi-optical techniques, free space techniques also work well at millimetre-wave frequencies. And of course, time domain spectrometers have been used for many years at terahertz frequencies. All three of those systems require a high level of operator skill and also a lot of time and effort to align and optimize these systems before they can make measurements that have any reliability. So there's a lot of skill and, if you like, bespoke capability which one really needs to develop in one's own laboratory. At the bottom of the slide there, I'm saying more recently there are now commercial materials characterization kits that have come on the market, and they can be used at both millimetre and terahertz frequencies. There's a company called Swister 12 in Switzerland that are making these systems that are quite literally plug and play systems that you can use without really high levels of skill, assuming you can use a network analyzer. So how do these materials characterization kits, MCKs, how do they work? Well, basically they rely on a network analyzer. They attach to the network analyzer extender heads that I showed you earlier. So at the end of the extender heads, we put one of these characterization kits, and they provide effectively a guided free space technique. In the bottom left there, you can see the 2 VNA test boards. Well, after that you have a horn section which uses a conical horn to launch the wave into a section of straight corrugated waveguide, which then launches this beam, a Gaussian beam for the materials measurement. It's an H11 mode, so it's a hybrid mode, but it's a very pure Gaussian beam, and so it can produce very reliable measurements. And you can buy these systems that operate anywhere from 25 gigahertz all the way up to 1.1 terahertz. You can see one there in profile on the right at the bottom of the slide, which shows the measurement planes where you insert your materials. I can show you it again on another slide here. This now shows the complete system on the left. There's the network analyzer in the background with a display unit on top showing the 4S parameters that are being measured. And in the foreground, you can see the 2 black box extender heads and one of these MCKs, the red unit, in between the two. And a close-up of that is shown on the right, which shows the materials characterization kit now with a sample of material inserted, which is this white insert here, which is probably something like PTFE or some other material. So the network analyzer with the extender heads launch S parameters, launch waves to measure S parameters. The materials characterization kit then uses that to measure the properties of the PTFE, and it quite literally takes the S parameters and translates them into parameters such as effective permittivity and loss tangent, etc. And it's all done at the push of a button, so it's a very simple and quick technique, and it works in real time. So it's a very powerful technique for making electromagnetic materials measurement, relying of course on network analyzers and these extender heads to give us frequencies in the millimetre and submillimetre wave range. For on-wafer measurements, it's a similar story again. We take the network analyzer, we take the extender heads, but now we need to translate that capability onto planar circuits. So this shows how we can measure planar wafers, flat wafers that are used in, for example, millimetre-wave and terahertz electronics, using things like gallium arsenide and indium phosphide, etc. So the photograph on the left is a probe station that we're using. It's a terahertz probe station, so it has very precise positioners for the probes that we use. We can position to within a micron accuracy on the wafer. In the background is the network analyzer with display unit. There are also 2 extender heads, and then the probe positioners are right in the middle of the photo. And then on the right hand side, the top right hand picture is a close-up showing the probes, which are going from rectangular waveguide down to probe tips, which are coplanar waveguide, where you have a ground and a signal and a ground line. And in fact, in the bottom right, you can see those probes landing onto a coplanar waveguide, which on this occasion has, it's difficult to see, but there's an on-chip graphene antenna which is sticking out of the coplanar waveguide line. So here we're able to characterize that antenna on wafer using the probes that take us from the wafer back through the extender heads in waveguide and then right the way back to the network analyzer. So again, now the network analyzer is enabled to do measurements like antennas on planar circuits. We need, of course, to have standards for these types of measurement, and really what we do here is we have standards which are actually on the wafers that we're measuring. This enables us to characterize the measurements at the tips of the probes as the reference planes. This is very important, so the measurements are referenced to where we land our probes, and there shown on the right is a Dominion microprobe capability, which is landing on a calibration wafer to do the calibration process. On the right here is a plot of typical performance. You can see about 6 dB insertion loss as shown by the red line, and the other lines below it are return loss figures, which are better than about 15 dB. Again, this doesn't sound impressive until you emphasize the fact that these are measurements taking place at and above 1 terahertz on planar circuits. So this is a really state-of-the-art as established by the Dominion Microprobes company for these sorts of measurements. Okay, I'm going to now move on to the second part of my talk, which is all about accuracy and traceability. This applies to measurements in general, and really my job as a metrologist is to understand accuracy and traceability whenever I do measurements. So I'm going to say a few words about those two key topics, accuracy and traceability, and try and emphasize why they're important. So for accuracy, as you remember at the outset, I said one of the main purposes of measurement is to help us make decisions. And really the reliability of those decisions and related risks depends on the uncertainties in the results of the measurement. So typically we show uncertainties, as I've shown you there, as a kind of a x plus or minus y, where the y is the uncertainty in the measurement, and gives us an indication of the amount of doubt we have about the accuracy of the measurement value x. So for example, if the uncertainty is low, if that value of y is small, then that implies we have high accuracy, and that means we can make more reliable decisions, both scientifically and commercially. So it's very important. I do have to emphasize that the plus or minus y bit, that symbol can also be used for other things. People will often represent repeatability or likelihood of error in measurements. That's not quite the same as uncertainty. In uncertainty, we're looking at the overall doubt about the quality of the measurement that we're making. So it's a more encompassing parameter. Now, in general, no two measurement values will ever be the same, even if you're measuring the same thing under the same conditions. If you have sufficient instrument resolution, you'll always get values which are different. And the question is the difference between, say, two measured values really significant? Does it matter? Do we need to worry about it? And really the only way we can answer that is by looking at the uncertainty in the measurement. When we have the uncertainty, then we can know whether two values are actually discrepant or whether they're effectively equivalent. So when we demonstrate equivalence, I'm going to show you here now that I've just depicted. It's basically an arbitrary measurement. It happens to be a voltage of something, and it's got the dot is showing a reading of about 1.5. And really there's no uncertainty shown there, so we don't really know whether that's a reliable value or not. We just know that that's the measured value. I've redrawn that dot now, and this time I've put a bar representing the uncertainty interval. So this one now shows that the range at which we would expect the true value for that measurement quantity or measurand, where we expect the true value to lie. So now we're making quantitative predictions about what we're actually trying to measure. So this is really important when we want to compare two measurements of the same thing. Well, why do we want to compare two measurements? Well, one measurement might be made by a customer and one measurement might be made by the supplier of the same device. And if those measurements don't agree and the disagreement is beyond the uncertainty, then rightly so, we have a situation which needs to be resolved. If the difference is within the uncertainty, then we would say they're actually equivalent and they're actually telling us the same story. So I'm going to give you some examples now of the answering the question, do the two measurements that are shown here, do they actually agree with each other? Well, at first sight, you might say, well, no, they don't agree. They've got different values on the scale. So how can you say they agree? Well, how we can say is if we do the work needed to understand the uncertainty in those two measurements, and then if we redepict them with their uncertainty, they might look something like this. Now, both values have uncertainty intervals, and you'll notice that they overlap each other. So that's saying the range of one measured value is within the range of the other measured value. And so essentially, this is showing agreement. Even though the actual values are different, the range of the values from the uncertainty shows that they are agreeing to a large extent. I can extend that further now. I can take the same values again, except if we had re-evaluated the uncertainty and it came out now what's shown on the right, you'll notice now those uncertainty regions no longer overlap. So we can no longer say that those two values are in agreement. So we would say they're discrepant, and if the two measurements are of the same device, then we would say they need to be investigated because they're not showing equivalence. That's the importance of uncertainty. It lets us determine if the values agree or not, and that means we can say something about if it's a product or if it's something that we're selling or buying, etc., etc. So uncertainty is really important. The other parameter I talked about was traceability. This is when measurements are linked to references. So this is also very important, that measurements are traceable to an independent reference. And the most important independent reference is what we call the International System of Units. So this is the system of units we have globally in the world that links all measurements back to the basic quantities such as the meter, the kilogram, the second, etc. If our measurements are linked to these base units, then they can be compared meaningfully with other measurements. If measurements are not traceable to the SI, then really they have very limited value, particularly in the world we live in where we have global trade and global science. We want to make sure that we're all linked to the same independent references. So traceability means that measurements are linked to other values elsewhere. And so this means that measurements made in different places can be compared. So again, you might have let's say a supplier, a company in the UK makes devices, they sell them to a company in Pakistan. We want to make sure that those measured values of those quantities are equivalent, and the way we would do that is establish traceability for measurements in Pakistan and traceability in measurements to the UK, and then the comparison of those measurements has some meaning. And so measurements that are not traceable really are not very valuable, because even if the values agree, because the references are different, then that agreement is very questionable. I'm going to show what is really a fictitious example of what happens when measurements are not traceable, and you'll have to take my apology. It is a fictitious example, and it's what I call the all-alone effect, and it happens on a procedure on the island of All Alone. Now, All Alone is an island, let's say it's in the middle of the ocean somewhere. They've got no GPS, they've got no time synchronization, so they've got no way of telling what the time is. And this story relates to a retired sea captain who lives in the town on the island, and his job is to guard the castle, which is at the top of the hill next to the town. And so every day he goes up the hill and he goes up to his castle and does a little procedure. So what happens is each morning the retired sea captain, it shows here on the left, he starts his day, he walks through the town and he sets his watch against the clocks that he sees in the local jeweller's shop in the town. That's fine. That means he's, if you like, calibrated his watch against the jeweller's clock. Then he climbs the hill to the castle where he works. And then one thing he does at the castle every day is he's got a cannon, and when it gets to midday, according to his watch, he fires the cannon so that everybody in the town can hear the cannon go off and they all know it's midday. So what happens is everybody, all the islanders, then set their clocks to midday because they know it agrees with the sea captain setting off his cannon. And that includes the jeweler in the local jeweler shop. He hears the cannon and then he goes round and sets all the clocks in his shop so that they agree with the cannon. So you can see the jeweler's now happy because he knows it's accurate, because he's corrects his measurements with respect to the cannon. But if you remember, the sea captain corrected his measurements with respect to the jeweler. So what you have is you have a sea captain who's traceable to the jeweler and the jeweler who's traceable to the sea captain. There's no independent reference for this measurement. So although these two measurements will agree with each other, because they've got no external references, then of no use beyond the people of the island. So if a visitor arrived, let's say somebody arrived from Pakistan and they had a GPS synchronized watch that they were using, the time that they would have was very likely to be very different from what was on the island of All Alone. And that's not because time itself is different, it's because the references that are being used are different. So in the one case, the island of All Alone, they're using traceability between the jeweler and the sea captain. In more general sense, we use things like GPS and primary references of time. So this is where independent references are very important. You might say, well, can this happen with real measurements? So I'm going to show you an example now of where it can happen in laboratories, in real laboratories. And this relates to providing traceability for network analyzers, vector network analyzers. And typically one way you can do this is by using a calibrated step attenuator. So you take your network analyzer shown here on the left, and you calibrate it, if you like, with respect to a calibrated step attenuator, which gives you known values of attenuation. Then you ask the question, well, where did the calibrated step attenuator get its values from? What was its references? So the calibrated step attenuator was calibrated using a precision attenuation measurement system, which is shown here on the right. But then you ask the following question, where does the attenuation system get its references from? Well, the attenuation system is calibrated by a network analyzer. This is a very common practice. And when you think about it, what's happened is the traceability route has gone round in a cycle again. There's no independent references. There's no link to the international system of units. So this is just like on the island of All Alone, which I spoke about earlier. They're traceable to each other, but then if there's somebody coming in externally, like a customer for the measurements or a supplier, then the good chances is those measurements will not agree. So how do we deal with that in practice? Well, an alternative method of providing traceability for network analyzers and microwave measurements is to use what we call impedance standards. So this is a different approach for traceability. And what we do is we calibrate the network analyzer using these impedance standards, which are shown in the bottom here. And basically they are reference air lines. So they're coaxial lines where the dimensions of those lines, the diameters of the center and the outer conductor, define what the impedance is of the line. And we provide that knowledge to the network analyzer so that it can be calibrated. So the network analyzer is calibrated with respect to the coaxial air lines. We can then calibrate those air lines, the impedance standards, with respect to dimensional standards. So on the left there, we have what we call plug and ring gauges, which are basically precision rods of metal and precision holes, which we can determine and characterize against dimensional gauge blocks, which is shown on the right. So we're passing the traceability now from the network analyzer through the air lines, through the ring gauge and plug gauges, through the gauge blocks. The gauge blocks we then measure with another one of these coordinate measurement machines, which we showed earlier, which is shown here on the left, and also a view again of the same system on the right. And the coordinate measurement machine provides traceability directly back to the SI base unit of the meter. So that means the measurements are ultimately linked back to the meter. So if we now present that traceability flow, it looks something like this. You can see the network analyzer gets its assurance from the airlines, which get their assurance from the plug and ring gauges, which link to the gauge blocks in the bottom right, which links to the coordinate measurement machine, which links us back to the international system of units. There's no circularity in this route of traceability. We're going back, linking the network analyzer to absolute scientific constants defined by our international system of units. And this is a very powerful method, because it means those network analyzer measurements are now comparable to any other measurements made anywhere else in the world. And in terms of a customer-supplier relationship, or even just comparing measurements in scientific papers, it means those measurements have a proven accuracy when they are stating the results. So that's really the end of my talk. I'm going to summarize, just go through some of the points I've covered here this afternoon. First of all, I hope I've demonstrated there's a very strong need to have new measurements in our industry and in academia to support new science. So in other words, when universities and industrial companies develop new science and technology, it's very important to develop new measurements that that can approve and assure the new science that's being made. This is currently happening in this so-called gap region we have in the electromagnetic spectrum, where electronics and photonics techniques are not working particularly well, and this has given rise to the need for capabilities in this kind of 0.1 to 1.1 terahertz region. I've shown examples where we've used network analyzers, VNAs, to measure the S parameters. I've also talked about how we can establish traceability for waveguide measurements using these VNAs, and how we can translate that into electromagnetic materials measurements using these characterization kits, the MCKs. I've also shown how we can translate those measurements onto on-wafer planar circuits, which are very important for our electronics industry. So this is how we are extending the utility of the network analyzer into different measurement modalities. And finally, I've talked about the value of traceability and understanding accuracy of measurements. That's very, very important, particularly for institutes like mine, which provide references to industry and academia for measurements. And so when we talk about establishing new measurement capability, we're not just talking about buying equipment from suppliers and switching it on and using it. We're talking about doing our own science and our own research into the metrology, the understanding of those measurements, so that we can be sure about the quality of the measurements that are being provided by the equipment. And that includes understanding the accuracy and also having a known uncertainty for the measurements, and of course the traceability to ensure their suitability for comparison with others. I'll finish with an acknowledgement, particularly to a new project we've recently launched in Europe, which is called the TEMP project. It's all about traceability for measurements at millimetre-wave and terahertz frequencies, and it's funding a lot of the research I've just shown you today in this presentation. It's a European funded project, but we do also encourage and welcome participation from organisations from outside the European community. And so if there isn't anything of interest, then please get in touch with me. I think I put my email on the title slide, so you're very welcome to contact me about the work we're doing. In fact, the project has a website, so you can see some of the output that we're generating. We're about 1 year into a 3-year project, so it's a very exciting time, and I think there'll be a lot of new measurements coming from this to underpin new science and technology, which is needed in our world for further developments in many areas and many different topics. Thank you very much to you all for your time. I guess it's this afternoon in Pakistan. It's morning here in the UK. I really appreciate your time today, and yeah, let's stay in touch. Thank you very much. Thank you, Noshawan.
Thank you very much, Professor Nick. It's really interesting talk, and you talk about the various aspects of metrology and the different type of equipment for waveguide, for on-wafer. Also, you show the importance of traceability. The example of that all-alone island was very interesting, just to understand the traceability and accuracy. So there are a few questions by the participants and a few questions also with me. So let's start them one by one. So the first question is, can you please comment on terahertz sources availability?
Wow, That's a very difficult question to start with. Terahertz sources, yeah, it's a major problem for this area. There's two types of source, and it was covered by my slide when I showed the electromagnetic spectrum, and on the left-hand side was electronics, and on the right-hand side was optics. When you translate that to sources, what we mean in electronics, as with the vector network analyzers, the way we're generating sources is through harmonic multiplication. So we take very reliable synthesized sources and then use those to generate harmonics, which is fine because we end up with very reliable frequencies in this terahertz region. The downside is that because you might be working off, let's say, the 50th harmonic, which is not an exaggeration, that's typical of what you might find at 1 terahertz. You might be on the 50th harmonic of a 10 terahertz, a 10 gigahertz fundamental. The power levels are minuscule. You're down at picowatts of power. So power is a real problem. If we go to the other side, if we go to optical techniques, then here we're using lasers. And so then it's often a case of mixing down using lasers to generate powers in this gap region from if you like, intermediate frequencies from 2 high frequency laser sources. There are other technologies, things such as quantum cascade lasers, which are actually designed to operate in this region and work very well with very good power levels. And I think that's an area of technology we need to watch very carefully, because there's a huge potential with quantum cascade lasers to really enable this part of the spectrum. So if I was a betting man, I'd probably be putting my money on quantum cascade lasers to win the terahertz source race that we're currently in.
Thank you very much. The next question is about the on-wafer calibration technique. So which one of them is more accurate, for example, SALT or TRL at these high frequencies? Or is there any other calibration technique that you recommend for on-wafer calibration?
Okay. It's when we're talking on wafer calibration, the technology is pretty well understood up to about 100 gigahertz. Generally, it's felt that TRL provides the most accurate calibrations, particularly multi-line TRL, so that you can both over-determine the calibration algorithms, but you can also extend the bandwidth of the capability. And there's been some excellent work done by colleagues at the laboratories in the USA, NIST, to provide those sorts of traceability mechanisms. When you go above 100 gigahertz, then you're really into the research domain of metrology. It's still an area for active research. People are presenting papers on different calibration techniques. A major concern at these frequencies is things like isolation, understanding and characterizing isolation between the probes. So, for example, using crosstalk compensation techniques that can rule out the signals that will travel from probe tip to probe tip without going through the device. This is a major problem, particularly at terahertz frequencies, because the wave will not just embed itself on the wafer and propagate as a genuine CPW mode. There are other modes, including airborne modes, that can really pollute the measurement fidelity.
Yes, that's very right. So the next question is, I think, about the calibration standard, I guess, is, can you please comment on parasitic capacitance inductance modeling for the calibration? Sorry,
parasitic capacitance, did you say?
Yeah, okay. Parasitic capacitance, yeah.
Okay, I think this would probably be a concern again with the on-wafer environment. Yeah. With the other two modalities I spoke about in Waveguide and with the materials measurements, we don't generally need to worry about parasitic capacitance and inductance. I think it's an issue with on-wafer, and again it would relate a lot to characterizing the properties of the probe. So one of the difficulties with on-wafer measurements is you not only have to understand the transmission lines on your planar circuit, you need to understand the probes that launch those waves. And this is where one would need to come up with accurate models for the capacitance and inductance terms. I would imagine that this is an area that the probe manufacturers are working on. At the moment, as a user of these probes, we tend to take their values as a good first start of how we characterize the measurements. We can then use self-calibration techniques to interrogate the reliability of those assumptions by using things like two-tier calibrations when the probes become part of the measurement circuit in one of those tiers, and then we can de-embed the probes from the overall structure of the measurement.
Yes, you're right. I think we can also, there are some models available in which we can optimize the values of these capacitor inductance to optimize the end results for calibration. Yeah.
Again, it's an area of active research. There's no definite answer at this stage. I think this is one of the exciting things about working in this area. We're still discovering things day on day, and that's, I think, what motivates most researchers.
Right. The next question is about 1 mm coaxial connectors for 75 to 110 gigahertz. The question is, do you recommend 1 mm coaxial connectors for 75 to 110 gigahertz band, or the band limited waveguide WR10 for measurements?
Okay, so the 1 millimeter coaxial connector, in my opinion, it's a very, very good connector. And of course, what it does give you, which none of the waveguides will give, is the broadband signal. So it's not just carrying 75 to 110, it will go DC to 110, and in fact above 110 with some reliability. So I would say the 1 millimeter connector is a very, very, very good transmission line, a very, very good interface, particularly if your application is for broadband. So you might have a communication system that requires that. I think with coaxial transmission lines, one needs to choose them dependent on what you're trying to do. You know, if you're building an amplifier which genuinely has broadband capability, it's no good putting a waveguide on its output, because you immediately limit the bandwidth that the user gets, and it's limited by the waveguide transmission line. So I think there's no clear answer to this. I think if you're after broadband capability, then you go down the route of the 1 millimeter connector. If you want banded capability, narrowband, then the waveguide suffices. There's another connector that's coming on stream that I would throw into the discussion, and it's the 1.35 millimeter connector. This is a new connector. I believe it's being championed by certainly a company called Spinner in Germany, and it's designed specifically for the E-band frequency range. So this is 60 to 90 gigahertz, I think. So it doesn't quite go as far as the 1 millimeter connector, but it's quite a rugged connector, and it's designed for use in the field, whereas the 1 millimeter connector is more of a metrology connector. You have to be careful when you use it. The 1.35 connector is more rugged, and is, as I said, it's tailored for the E-band communications applications that are coming on stream now. So I would recommend checking that one out. I think you could either do a Google search or contact people at Spinner, and that's a very exciting new development in the area of coaxial technology.
Yes, the next question is, do you think investigating a contactless probe technique will be more useful in this frequency range?
The short answer is a definite yes. If we're talking about contacting wafers, then if we could somehow get the electromagnetic signal onto the wafer without contacting, that has to be the more desirable approach, because really you lose a lot of signal fidelity at the point of contact. Not only do the contacts give rise to all sorts of things like spurious modes, reflections and surface waves, it can also damage the circuits that you're landing on, because probing is very much an invasive technique, and so it can give rise to imperfections just from the act of probing. Nobody wants that, and that's particularly problematic where you have to probe with, you know, micron precision in order to get something sensible. So yeah, absolutely. I think non-contacting capabilities where you might want to focus a wave onto a probe and have a coupling mechanism which is non-invasive, that would be fantastic. That would be something really worth looking into, and I'm sure there are researchers that are looking into that. But I think at the moment it's still in the research domain rather than in production. So a lot of opportunity there.
Yes, you are very right. I think working with on-wafer measurements is always a challenge. Landing it properly and making a proper connection is not
Yes.
an easy job. And on the other hand, the on-wafer probes are also very expensive. So there's always a possibility of damaging the probe. Yeah.
They're very expensive, and the higher you go in frequency, the more fragile they get.
Yeah.
So they're difficult to use at lower frequencies, but at these very high frequencies, you can't afford to let the probes slide on the circuit when you land, which is a technique used at lower frequencies. If you do that at submillimeter waves, the probes will break. So
Yeah.
very fragile, very difficult. And so, yeah, if we can do it without contacting, then I think that would open up an entire new area of metrology, and you know, a new paradigm for making these measurements.
Yeah, that's true. I think the next question is related to our current discussion, that what are the dimensions of on-wafer probe tips, the size and spacing, maybe at these high frequencies?
You mean like the pitch size for the probes?
Yeah.
I can't remember. Clearly, what happens is that as the frequency goes up, the spacing between the lines on your wafer, your ground signal line, they come closer together. If I was to guess, around about a terahertz, we're probably down to about 20 or 30 micron pitches in order to ensure, you know, relatively pure CPW modes are launched. So yeah, but of course this is taken care of by the probe manufacturers, and there's some very good ones. I showed you Dominion microprobes. There's also GGB that make these probes, and they do a really good job. So I think that's the domain of the probe manufacturers.
Yes, Professor. There's another question that I would like to ask you, that you should comment about the redefinition of the SI units, that is quantum realization. So how you link this work with the redefinition?
Okay, well, absolutely, and of course that's been a huge activity in recent years by national metrology institutes like NPL, but many such institutes from around the world, and I'm sure you're aware that this has resulted in the redefinition of at least 3, possibly 4 of these base units. So they're now defined in terms of quantum phenomena rather than physical artifacts. So we've lost the kilogram as a lump of metal, and it's now defined in terms of quantum phenomena. So this makes the whole SI system much more reliable and much less subject to change, because we're relying on fundamental physical laws. Where I sit, I'm very much downstream from that activity. I'm an end user of the SI, so I don't define those base units. Certainly colleagues of mine here at NPL do, but they're not working in my laboratory. They're working in the area of quantum technology, time and frequency, etc., defining, you know, quantum realizations of the second, the meter, the kilogram, etc. And that's been some really excellent work by many scientists from around the world. And I think we as beneficiaries, as end users, should offer them a huge amount of thanks for that work, because it means our science will be that much more reliable when we take it forward. And so I can't comment on the actual realization, but what I can say is, as an end user, I'm very thankful for the, if you like, the implementation of a truly quantum-based SI system. And I think we as an entire human species will benefit from that for many years to come.
Yeah, definitely, because it will definitely increase the reliability of the measurements as well. So the next question is it true to say that at higher frequency, the measurement interval of the true value is smaller? That is, the uncertainty increase at high frequencies?
Oh, almost invariably. Whenever you go up in frequency, if you like, everything gets worse. The uncertainty generally degrades. So those error bars, if you like, that I showed, you expect those to get larger as you go up in frequency. This is because the error sources have more of an impact when you go up in frequency. So to bring it to the waveguides I was showing you, if you have a displacement of say 10 microns, well, at 10 gigahertz, that's a negligible effect because the waveguide is so much larger. But when the waveguide is only a few hundred microns, and then you have a 10 micron displacement, that can be a 10% error in your measurements without any other considerations. So basically, the same size of error gives you a much larger uncertainty as you go up in frequency. And as a practitioner of those frequencies, there are other things that get worse as well. We've spoken about the amount of power from the sources. That gets worse. That gives you more uncertainty. We've talked about the problems with probing and how pitch size has to come down, and the probe skating that it does has to be much less. And the one that the managers really don't like is the cost of everything goes up as well. So that's another bad one to throw in the mix, along with fragility of components. So things perform less well, they're more expensive, and they're more likely to get damaged. So when you tell that to your manager, they don't really like to hear that message. So you need to address that one up before you mention it.
Yeah, that's very true. I mean, I remember working with, I think, WR03 waveguide at NPL, and there's a slight misalignment between the waveguides and also the dimensional uncertainty. Everything contributes to the final aim. So it's really
does.
at high frequency. Yeah.
Yes, indeed.
This is, I think, the last question. So does the traceability of the measurements also accumulate uncertainties?
Yes, it does. It does. In fact, generally, as a rule, with each step that you have in your traceability path, each one has to inherit the uncertainty from the step before it. So if you like, the uncertainty can only get larger as you move away from the primary reference. So in terms of the route I showed from the SI, the definition of the SI units, as you move away from that, when you use your coordinate measurement machine, well, that machine brings in its own uncertainty. When you use your gauge block, that has its own uncertainty. So the uncertainties convolve, if you like, and inevitably get larger. So as a general rule, if you're trying to produce really accurate measurements, you want to keep those traceability links as few as possible. So the one I showed you on the slide was actually a very realistic one. We use network analyzers, we use the reference airlines, the coaxial lines, then we go back through gauge blocks through the coordinate measurement machines. So about 4 or 5 steps before we get back to the quantum realized meter that is our reference.
Yes, very true. If I remember, the inter-comparison between different labs across the world also gave us a very good understanding analysis of how accurate or how reliable is one measurement as compared to the other. So that's why I think there are always a number of inter-comparison of calibration standards are going on
yes,
with the labs. Yeah.
That's right. Yeah, that's a very good point, Noshawan, that you make there, because things don't stop at a national lab like NPL. One of our duties and one of our key responsibilities is to compare our measurements with other nations' national measurement laboratories. And this is done, as you said, through intercomparison. And there's an active program of intercomparisons happening all the time in different parameters that are used in the physical sciences. And this is all monitored and kind of controlled by the International Bureau of Weights and Measures, which is an international entity which controls all areas of metrology at the very highest level. So that's very important because, as I said, we need to not only just demonstrate but also verify that what we've done is actually defensible when we talk about uncertainty.
Yes, very right. So with this, I would like to thank you for your talk, for your time, and it's a really pleasure for us to host you, and hope to see you again at some other forum as well.
Indeed, and thank you so much for inviting me. It's been a real pleasure for me to talk to you today and people on the line. It's just a pity that we can't be face to face on this occasion with our current global health problems, but you know, maybe that'll come another time and hopefully soon. Yeah,
hope to see you in Pakistan very soon, maybe also in the next conference that we are planning for 2021.
Yes, that sounds very interesting.
Yeah. Thank you very much, and have a nice day, and see you later.
Thank you, you too, yes. I'm assuming you'll sign me out, so thank you very much and goodbye everyone.
Thank you. Goodbye. So